Welcome to The Explainer. Today, we are diving into a seriously fascinating new research paper that reveals how the open source community is actively closing the AI data gap. And they're doing it in a pretty ingenious way, by literally turning digital trash into training gold. Look, if you've been following the AI space at all recently, you already know that the quality of the data fed into a language model is, without a doubt, the single most important factor in how well it performs. But what happens when you just run out of pristine data? Well, you have to make your own.
Here's a quick look at our roadmap for today. We're going to cover the data quality gap, how researchers are transforming code data, the incredibly rigorous four-stage pipeline they use, how they apply this to rewriting math data, the dramatic performance gains they achieved, and finally, what this all means for the future of open data. Let's just jump right in.
Section 1. The data quality gap and the core problem with open models.
Okay, so let's set the stage here. The massive, glaring issue right now is that the leading closed-weight models, the frontier models from the giant tech companies, have a monumental advantage. And that advantage is their secret, highly curated training data. The open source community, on the other hand, just doesn't have access to that same caliber of code and math data. They're relying heavily on massive but honestly pretty messy public web scrapes. This creates a growing quality gap that's putting a hard ceiling on how smart open models can get at complex tasks. So the absolute million-dollar question for the open source world is, how do we fix bad AI training data? Data sets out there right now, like the Stack for Code or FiMath for Math, they use rule-based extraction for massive web crawls. Sure, they might use some basic scoring to filter out the absolute worst junk, but they still end up with tons of noisy, redundant, or just poorly formatted data. It's a huge bottleneck.
And this is where the researchers introduce a total paradigm shift. Traditionally, the go-to approach has been what we call exclusionary filtering. Basically, you score the data, and if a snippet gets a low score, you just toss it in the bin. But think about that for a second. That wastes a massive amount of potentially useful information. Plus, the data that does survive the filter still has lingering issues, like missing context or weird naming conventions. Instead, this new paper proposes a transform and retain method. Rather than throwing out the bad code, they use large language models to actually rewrite and refine it. They're eliminating the noise, maximizing the utility of the data, and preserving the core semantic context. So the mantra here is, you don't just filter it, you fix it.
Moving to Section 2, transforming code data and introducing a data set called Swallow Code.
So the researchers took this whole rewriting philosophy and unleashed it on a massive Python dataset, specifically a chunk of the Stack v2. And what they produced is a brand new, openly licensed pre-training dataset that they named Swallow Code. It's an absolutely massive 16.1 billion token corpus of highly refined, cleanly rewritten Python snippets. And the results are wild. When they tested this new dataset against other major Python-only sets, like StackEDU or the original Stack v1, under a really strict 50 billion token training budget, the accuracy gains were just undeniable. It hits the highest pass-it-once scores on HumanEval, which is the gold standard benchmark for coding proficiency. This isn't just some tiny incremental bump. We're looking at a completely different, much steeper learning trajectory for the model.
Section 3. The four-stage pipeline. Let's look under the hood.
Now you might be wondering, how do they actually pull this off without accidentally destroying the underlying value of the code? Well, it wasn't random. The journey starts with over 41 million original, noisy Python samples. From there, it's systematically whittled down and transformed into highly optimized, self-contained examples. They used a rigorous, empirically tested four-stage pipeline. They definitely didn't just dump millions of raw files into an LLM and cross their fingers. It's a carefully staged gauntlet.
Let's break down that gauntlet. First up is syntax error filtering. They literally just try to compile the code using Python's standard tools, and anything that crashes is immediately discarded. That drops about 10% of the junk right off the bat. Second, they run linter-based filtering using Pylint. So if the code technically compiles, but it's structurally a mess, like throwing endless warnings or having 10 times more comments than actual code, it's out. Then, in stage 3, the magic happens. This is the Style-Guided Code Rewriting stage, or SGCR. Here, they actually bring in an LLM to rewrite the code so it strictly follows the Google Python style guide. Finally, stage 4 is Self-Contained Optimization Rewriting, or SCOR. The LLM goes back in to optimize the actual algorithms and resolve any missing dependencies so the code can run perfectly on its own.
The contrast between the filtering stages and the rewriting stages is absolutely fascinating. When you just do the basic syntax and linter filtering, you get a modest bump in model performance, maybe 1 or 2 points on the HumanEval benchmark. I mean, it helps clear out the garbage, but it has a hard limit. But when you apply those 2 LLM rewriting stages, the performance goes vertical. The style rewriting stage jumps performance by 7 and 9 points just by unifying variable names and adding proper type hints. Then the optimization stage adds another 5 to 6 points by actually swapping out slow algorithms for faster ones. Combine them, and that LLM rewriting adds up to a staggering 14 points of improvement.
Section 4. Rewriting math data. Taking this from fine math to swallow math.
The true test of any great methodology is whether it works in more than one place. The researchers wanted to prove that transform and retain wasn't just a fluke for coding, so they brought it over to mathematics. They took an open math corpus called FineMath 4+, which is notorious for being heterogeneous and noisy. Think math equations buried underneath irrelevant web junk. The goal was to create a refined dataset called SwallowMath. Simple filtering wouldn't work here, so they prompted a powerful LLM with 5 very specific strict rules. 1. Rip out all the residual web headers and footers. 2. Delete irrelevant metadata like timestamps. 3. Restore any missing context from incomplete questions. 4. Rewrite the actual mathematical derivations to be concise but comprehensive. And 5. Reformat everything into crystal clear step-by-step solutions. It's the exact same philosophy used for the Python code, just brilliantly adapted for the heavy logic of mathematical reasoning.
Which brings us to Section 5, the dramatic performance gains.
Okay, it's time for the hard evidence. The true climax of this paper is the real-world impact this methodology has on actual model benchmarks. To test this fairly, the researchers did continual pre-training on a standard Llama 3.18b model. They kept all the parameters the same, the non-target data the same, and strictly capped it at a 50 billion token budget. The only thing they changed was swapping in their rewritten datasets. The math results are just staggering. By substituting the baseline data with the new SwallowMath corpus, they saw a 12.4-point jump on GSM-8K, which is a benchmark for grade school math. Even crazier, they saw a 7.6-point jump on the notoriously difficult math benchmark. That is a massive, massive leap in reasoning capability, all achieved purely by engineering better training data.
And if we circle back to the code domain, the final results for Swallow code are just as impressive. Compared to the StackEdu baseline, which by the way is already a heavily filtered, high-quality dataset, training with the rewritten Swallow code boosted those pass-at-1 scores by 17 full points on Human Eval and over 16 points on Human Eval Plus. Remember, this was all within that exact same 50 billion token budget. So what's the takeaway here? It conclusively proves that a smaller amount of incredibly high-quality, explicitly rewritten data is vastly more effective than a massive mountain of data that's merely been filtered.
Section 6. The future of open data. Limits and potential.
Now, as undeniable as these performance boosts are, we have to keep it real and talk about the limitations. We know rewriting works, but doing it at scale is tough. First off, this code pipeline leans heavily on static syntax checkers and linters that are highly optimized specifically for Python. If we want to expand this to dozens of other programming languages, we're going to need a lot more specialized tooling. Second, we can't ignore the incredibly high computational cost upfront. Having an advanced LLM meticulously rewrite billions of tokens requires some serious hardware and money. And finally, there's the really interesting risk of inherited stylistic quirks. Because a specific model, in this case Llama 3.370b Instruct, did all the rewriting, the resulting dataset might actually absorb that model's specific formatting habits or problem-solving preferences. And those quirks could easily get passed down to any future model trained on this data.
But, and this is a massive but, the authors point out something crucial. That huge, painful initial compute cost to rewrite the data, it actually transforms into a durable asset for the whole community. They didn't just publish a theoretical paper and walk away. They totally open-sourced the Swallow code and SwallowMath datasets, all the specific props they engineered, and the entire pipeline codebase. This means anyone, any developer, any startup can take this, reproduce it, and build on top of it without having to foot the massive compute bill for rewriting those billions of tokens themselves.
Which leaves us with a final, pretty provocative thought to chew on. If open-source developers can continuously refine, update, and freely share these incredible alchemy recipes, literally turning noisy web scrapes into pristine, high-signal training data, how long until they completely close that quality gap with the major tech giants? We are officially moving from an era of just hoarding the biggest datasets to an era of deliberately engineering data quality. And honestly, that might just level the playing field forever. Thanks for joining me on this explainer, and I'll catch you next time.